Namaskar students, my name is Shashank Shekhar. So today we will start the CFT. So if I talk about the previous class, so in the previous class we have studied VBT. So how does the hybridization take place? How does the formation of inner orbital complexes take place? So we have seen that. So in the today's class, we will study about CFT. Why? Because of the limitations that we have seen. What were those limitations? So first of all, it was not able to explain the color phenomena. Second, it does not give any quantitative explanation about the magnetic properties. Third is you can say about this that it does not explain that when it will form the weak field, when it will form the strong field, what about ligands and all. So it takes none of these into consideration. So CFT does, and I think it provides a very good explanation to most of the phenomena that our coordination compound undergoes. So we will study about coordination compound today. Okay, coordination compound. I would not say coordination compound. We will study about CFT in coordination compound. So as I've told you, so these are the topics that we will cover: the crystal field theory first of all, and then the crystal field splitting in octahedral complex. So there is a kind of splitting that takes place in of the d orbital for different type of complexes, octahedral, tetrahedral. Then we'll study about the color. Okay, and of course it has some limitations, and then the MOT comes and explains these limitations, right? Then we'll study about metal carbonyls and about the application of coordination compound. So why are we studying this coordination compound? So let's start our today's class. So first of all, CFT. How do we know how it is CFT defined? So earlier we have seen that, okay, overlapping of orbitals is taking place and hybridization is done, okay, but CFT takes none of those into consideration, and instead of that it considers electrostatic model. Okay, so it is completely based on electrostatic interaction between the metal ion and our ligand. How does it do so? See, we have ligand, okay, so ligand can be anionic, okay, and neutral. So if it is anionic, then in case of anionic, they are taken as point charges, okay, point negative charges. And in case of say neutral molecules, they are taken as dipole, where the negative part of the dipole. So what is dipole? It is dipole is a consisting of both positive and negative charge, which are separated by some distance. So the negative part of the dipole will interact with the metal ion, because metal ion is positively charged, and this interaction between the negative and positive charge is the basis for forming the CFT model, right? And since there is interaction, the formation of bond take place between the metal and ligand as a result of this interaction. Clear? So is this point clear? So our crystal field theory is based upon the electrostatic field. Okay. Second, if it is a neutral molecule, then it is taking as point dipole, in which the negative part participates in the bonding with the metal ion. And if it is a negative charge, then in case of that, it is taken as point charge, and then this point charge interacts with the metal ion. Now, in case of transition metal, so the transition metal are the one which is forming the coordination compound, and in the transition metal we have d orbital. Now this d orbital, these 5 d orbitals are completely, okay, these are completely turned into gaseous atoms. So they are completely degenerate in case of gaseous metal atom or ion. So whether it is an atom or is ion, so in case of isolated gaseous atom, what is isolated? Isolated means they are far from any interaction. So in case of isolated gaseous atom, we cannot see, we will not see any we will not see any difference in energy of the 5 d orbitals. Clear? So is this point clear? Okay. Now next, what will happen? This degeneracy is maintained if a spherically symmetrical field of negative charge surrounds the metal ion. Now what will happen? The negative part of the dipole, if it is a dipole in case of neutral molecule, and if it is an ion, the point negative charge, they approach, say all of them approach. So it create a sphere of negative charge. So in that case also, the you can say the d orbitals are still degenerate. The 5 d orbitals are still degenerate. Now, but as approach closer and closer, right? Say that what will happen? Splitting will take place. This d orbital, they split into different energies, right? So some set of orbitals will have some energy. The next set of orbital have some different energy. So this 5d orbital are no longer having same energy. Clear? So due to the asymmetrical approach of the ligand, we can see that a degeneracy of the d orbital is lifted, and this results in splitting of the d orbital. So this is the case of splitting. Now the pattern of splitting depends upon the nature of crystal fluid. So let us just try to explain this in the form of illustration. So what it is saying that now this splitting, how this will split, this will depend upon the crystal field. The crystal field means the field that is created by the ligand, right? So in an octahedral coordination entity with 6 ligands surrounding, there will be repulsion between the electrons in the metal d orbital and the electron of the ligand. So as this will approach, now the d orbital has electrons and the ligands which are approaching, suppose we are taking octahedral complex. So 6 ligands will approach because the coordination number of say our octahedral is 6. So 6 ligand will approach. Now 6 ligands approach through their molecular orbital, their atomic orbital, and those atomic orbital will contain electron. So the electron in the orbital of the ligand and the electron in the d orbital of the metal, they will have a repulsion, right? And such a repulsion, when the metal d orbital is directed toward the ligand, then it is away from the ligand. What it is said? So if the metal d orbital is directed towards the ligand, suppose if there is a case that the approach of the ligand and the direction of the d orbital both are in the same direction, then in that case the repulsion will be maximum, right? And suppose it is now consider dx, right? So they are between the axis. Suppose the ligand are coming along the axis. Now in that case, what will happen? The direction of the approach of the ligand and the direction of the metal d orbital both are different, and that will result in less repulsion. Okay, so this is the difference in case of approach, right? So this should be kept in mind. I will use this concept about the case of approach. Okay. Now thus the dx square minus y square and dz square. So it is talking about the two orbitals which are along the axis. Okay, so if you just remember, I have told you that the dz square and dx square minus y square, these two orbitals are along the axis. So if I just draw it again, suppose I am drawing dx square minus y square. So this will look like this. Okay, one here. Okay, so let me erase them all and draw it on the 4 axis. Here, this one, and this one. All right. So suppose this is x-axis, and this is y-axis. So we can name it as dx square minus y square. So this is dx square minus y square. As compared to this, the other orbitals, suppose dxz and yz, they are between the axis. Suppose this is your axis. Okay, this is your axis. So here will be one orbital. Here will be one orbital. One will be here, and one will be here. So this is, suppose it is x, and this is again y. Then this is dxy. Now both these orbitals are having the same shape. Okay, you can see very clearly they are having same shape. But what is the difference? The difference is that they are not along the axis. This is along the axis, and this is not along the axis. Okay. Now suppose if in case of say our octahedral complex, it is said that the ligand will approach along the axis. Okay, the ligands approach along the axis. Now as a result of it, the repulsion is increased for this orbital and not for this orbital. Okay, of course it will have repulsion, but as compared to this, which is already along the axis, this will suffer more repulsion. And same is the case of dz square. Okay, so dz square is in this shape. Suppose this is z axis. This is termed as dz square. Now, both of these orbitals are along the axis and they will suffer the maximum repulsion. Okay. As a result, they will be lifted in energy. Okay, they will be lifted in energy. Whereas the dxy, dyz, and dxz, since they are between the axis, they will be lowered in energy relative to the average energy of the spherical field. So initially, they all were having the same energy spherical field. Now, when the ligand approach closer and closer, and since in case of octahedral, the ligand approach through the axis, therefore, they will that dx square minus y square and dz square, which are already along the axis, they will suffer more repulsion, then they will be higher in energy. Whereas the one which are lower in energy are the one which is between the axis. Thus, the degeneracy of the d orbitals has been removed due to ligand electron metal repulsion, and this will result in two sets of orbitals, that is T2G and EG. Now, what is T2G and EG here? So T means triply degenerate, means 3 degenerate orbital will be on one set, and E means doubly degenerate, means 2 set of orbitals will be on one set. And this G that is mentioned here, what is this G for? This is for G-rate, G-rate and un-G-rate. So we'll see it. What is G-rate and un-G-rate? I will just try to explain it when we'll get the complex. So if I give you just a click of it, so if you just look at the octahedral, you can clearly see that it is symmetrical in shape. Okay. So if I am talking about the point of inversion, if you go from the, suppose you take the center, you go up, you go down, you will see the same thing is there. Okay. One lobe is up, one lobe is down. Similarly, if there is one lobe, in the opposite of that, there will be another lobe. So it is completely symmetrical. So in such case, we call it as that it is having a G-rate. Okay. It is G-rate in nature. Clear? So this is termed as G-rate. So if I take the tetrahedral, it is not the case. So one lobe is there on the upside and 3 tripods are there. So if you just go below, there will be no lobes. Okay, clear? So it is not G-rate. Clear? So this is the meaning of the symbol. Now, as they will get splitted, there will be 2 sets of orbital, and the difference between the 2 sets of orbital is termed as delta O, where the O represent octahedral. Okay. So if you talk about the upper orbital, then they are lifted up by the energy of 3/5. Okay. So 3/5 delta O, it is upside, and 2/5 delta O, it is downside. So we'll look at the picture and get a more clear picture. So this is our picture. Now, there first of all, there is no field. Okay, no ligand field is there. Now, as the ligand field approach, first there will be increase in energy of all of these 5 orbital. Now they are in a symmetrical field. You can see that this is free metal ion. Okay. Now there is a you can say a charge, but it is spherical in shape. But now as they come closer and closer, there will be splitting. So 2, that is dx square minus y square, will go up. This is dx square minus y square, and this is dz square. So they will go up first of all, and 3 will come down. dxz, dyz, and dxy. This 3 will come down. These 2 are, and the difference between these 2 means there is a difference of delta O. Means the energy gap between this set of orbital and this set of orbital is delta O. And this is called as barycenter. These 2 orbitals are raised by an energy of 3/5 delta O. Okay, and this is dropped by an energy of 2/5 delta O. If you add both of this, 3/5 plus 2/5, it will give you 1 delta O. Means these 2 orbitals are raised by an energy of 3/5 delta O, and these 2 are dropped by an energy of 2/5 delta O. See, as compared to the VBT, this one is completely rationalized. So this is due to the ligand, they come in this fashion, and then the splitting take place. Whereas in case of VBT, we do not have any such explanation. We say that okay, the hybridization take place and we get a set of orbital. And one more important thing here, that the conservation of energy is completely maintained. The amount of energy is completely maintained. Okay, there is a conservation of energy. If you add all of this, you will get this energy back. Clear? Now, next, moving on to the tetrahedral splitting. So this was all about the octahedral splitting. Now you can see one more thing. There are 2 sets of orbitals, so it is called doubly generate, and this is for G-rate. Similarly, this is 3 set of orbitals are having same energy, so T2G, triply degenerate, with a G-rate sign representing that octahedral is symmetrical in nature. So is this clear? Okay. So next we'll move to tetrahedral splitting. So let us move to tetrahedral. The case of tetrahedral is just opposite to the octahedral. So we'll see it how it happens. Now some important points regarding octahedral is that the crystal field splitting delta O will depend upon the field that is produced by the ligand and the charge on the metal ion. See, this is very important point. Okay. So the ligand alone is not defining all of the things in this case. Okay. Why? Because this is the electrostatic model and it is totally dependent upon the electrostatic interaction. So the charge on the metal ion plus the field that is produced by the ligand will decide, the negative field that is produced by the ligand will decide the amount of splitting, that at what amount it will split. Now some ligands are able to produce strong fields and some are able to produce weak fields. So depending upon the strength of the field that is being produced, they are divided into two types, strong and weak field. So we will see which ligands form strong field and which ligand form weak field. Although there are some exceptions to it, and the exception is the reason behind exception is the metal ion, because metal ion is also involved. And to just say put a rule that is completely based upon say metal and ligand both, that is very difficult. But we'll try to rationalize each and every point. Clear? And I assure you that once I give you the idea about which one will form high spin, which one will be the weak field, okay, so then you will not make mistake, okay, and you will not be confused that which will form weak field and which will form strong field. Okay, so for that we are given a series, okay, for series that will define that this set of ligands are strong and this set of ligands are weak. Okay, so here is the series. The weakest one is the I minus and the strongest one is the CO. Okay, is this clear? Now this is the series I minus, Br minus, SCN minus, Cl minus, S2 minus. Now I suggest you to try to learn this. Okay, so this is very important. So up till this we have strong field. Okay, so this is strong field ligand. These are strong field ligands. Whereas NCS, starting from NCS to CO, they are, sorry, this is weak field, not strong field. These are weak field ligand. And after NCS, from NCS to further, we have strong field. Again, I am saying weak field and a strong field is a mutual interaction between this metal and the ligand. But if in the general case we talk about, then majorly it is decided by the ligand. So I am just trying to bifurcate this in strong and weak field. So what will the strong field do and what will the weak field do? We will see it. Okay, we will see it right now. Now, suppose let us assign the electron in the d orbital of the metal ion in octahedral complex. Obviously, the single d electron occupies one of the lower T2G orbital. In D2, D3, the d electron occupies the T2G singly in accordance with the Hund's rule. So if you just try to draw it, the splitting, if you just try to draw it, the splitting, this will look like this. Okay. So if you talk about D1, suppose I'm talking about D1. So according to Hund's rule, this one is higher in energy. This is the order of energy. Okay. So D1 will be this. If I talk about D2, then following the Hund's rule, first this one will be filled and then this one will be filled. Okay. This is what? This is D2. This is D1. And this one is D2. Similarly, if you have D3, it will go like this. One, two, and three. So this is what? This is D3. Clear? So up till this, we don't have any problem. Okay. The problem comes when we have to fill the orbital in the another shell. Right? So this is D3. Now when we move to D4, the problem arises of spin, low spin and high spin. So for D4 ions, two possible terms are there, patterns are there. the 4 orbital can either enter the T2G first case, or it could be in EG, or it could pair up in EG. Now, according to your, say, Hund's rule of maximum multiplicity, it should have been paired up. But there is another factor of energy. So let me draw the two cases for T4. So first case is pairing. So 1, 2 and 1, 2, 3. This is a splitting. Suppose the fourth electron pairs up. Okay. And the second case is that they do not pair up and go on the upper orbital. Right? This energy gap between both of this is delta O. This should be always reminded of. Okay. Now, two cases arise. First is pairing and second is not pairing. So what will be the deciding factor? Say when it will be paired and when it will not be paired. So for that we have a rule. Okay. For that we have a rule. What is the rule? So again, let me draw it again. So 1, 2, 3. Okay, the first case, second case, for both for T4. Suppose in this case we have pairing. The fourth electron pairs up. Where in this case the fourth electron goes up. So the major deciding factor is delta O and delta P. Now if you see here, in case of pairing, we should have some pairing energy to be employed to pair up this, because they both are negatively charged. If they are to be put in the same set of orbital, then the pairing energy is implied. Okay. And suppose delta O is greater than P. Okay. Delta O is greater than P. Means to bring the, or to put the electron in a higher energy level, that is on the delta O, because the energy gap is what? Delta O. So suppose I have to put this electron on this orbital, but the pairing energy is lower, means the energy required to pair it is lower as compared to put it in the upper case. Okay. So we know that it goes, or it always goes to minimum energy. For that case, what will happen? Rather than pairing, rather than going to the upper orbital, it first pairs up this. Why? Because pairing energy is low as compared to the energy gap between these two. But second case can arise that delta O is less than P. Okay. Means to pair up the electron, we will require more energy rather than to put it on a higher energy. Then in that case, what we will see? We will see that pairing will not take place and it will go to a higher orbital. So same thing written here. So if delta O is less than P, okay, then in that case, we call it as weak field. So why it is written weak field? So delta O is less than P means the ligand that was present there has splitted the energy with delta O is less. Okay. Delta O is less means the splitting is very weak. Therefore, we call it as weak field. Weak field ligand means the ligand that was used here is a weak field ligand. Why is it so? Again, I am telling it. Since the stabilization energy delta O is less than the pairing energy, means the splitting is less, and splitting is done by the ligand. So ligand is a weak field ligand. Whereas in this case, the delta O is very high as compared to the pairing energy. So rather than going to a higher energy, it gets paired up. So this delta O is high. Okay. And for that reason, we do not see any higher energy electron. Means the splitting is done by the ligand. So ligand is a strong field ligand. So is this point clear? So this is a very important point. Okay. So this should be clear in your mind. Strong field ligand and this is the weak field ligand. Clear? Now, if delta O is greater than P, it becomes more energetically favorable for the fourth electron. Means the fourth electron can be now more energetically stable if it occupies a T2G with configuration T2G4. Means pairing will take place. Okay, so I have told you if delta O is greater than P, then pairing will take place. In that case, it called as low spin complexes. Okay, so strong field will form low spin complexes. The low spin complex, and weak field will form high spin complex. What it will form? It will form high spin complex. Okay, so this is about the case of strong and weak field, and we have already decided a table regarding when it will be strong and when it will be weak. But when very important point is to be noted here. Okay, what is it? See, first the ligand is deciding factor, but this is only the case of 3D. Okay, so if the metal is from 3D transition state, then and then only we will look upon this thing. In case of 4D and 5D metals, they all form weak field. Okay, sorry, they all form low spin complexes. So this is very important to notice that in case of 4D atoms or 4D metals and 5D metals, 4D series and 5D series, all the metal ion will form the low spin complex. And why is it so? Because the energy gap between the splitted orbital is less. Where in case of 3D, the strong and weak field ligand are approached or they are looked upon. But there is again an exception for CO3 plus. For CO3 plus, only fluorine will form high spin. Okay, for CO3, if the ligand is fluorine, only fluorine, only and only fluorine, then it will form high spin. And except fluorine, if any other ligand is present, they will always form the what? Low spin complex. Okay, so this should be clear. Okay, this is very important point. Now, apart from this cobalt 3 plus, if you have to look for weak field and a strong field, you will simply look upon what? The spectrochemical series. Clear? Okay, very clear. Next is we will move to tetrahedral complex. Okay, we will move to tetrahedral complex. Now, one important thing is that delta T is 4/9 of delta O. So, delta T is smaller than delta O. And this is the reason that tetrahedral complex will always form high spin. Okay, means first all the d orbital will be singly occupied and then the pairing will take place. Okay, why the reason behind it is that delta T is very less than delta O. So this is very important point here. Okay, so this should be noticed. Now the G subscript is used for the octahedral square planar complex only, which has a center of symmetry. I said you this, but in case of tetrahedral, we do not have any center of symmetry. Therefore, we do not have any G sign. Consequently, the orbital energies are not sufficiently large for forcing pairing, and therefore low spin are rarely observed. Okay, they are not observed, and you will not see an example also. You don't have to worry about it. And last point is, because of the absence of symmetry, they lack symmetry, so they are non-G-red. So we have to drop this G word here. So see, it is written only T2 and E, not T2, G and EG. So this is very important point. Okay, so this small things make up the coordination. Clear? So this is about tetrahedral. Now the confusion arises when the student are asked, okay, in case of coordination number 4, when it will be square planar complexes. So see, student, for D8 configuration, okay, for what? For D8 configuration, if the coordination number is 4, then there is a chance that it will form, and I would say not is a chance, always it will form square planar complexes. What it will form? Square planar complexes. We do have many examples like Ni, PD, PT, say they all are the one which are more accurate towards a square, or they are more adapted towards square planar complexes. So I would suggest you should stick to this D8. So once you see a D8, it will form square planar complexes in case of 4 coordination number. Whereas in the other case, you will stick to your tetrahedral. Okay, clear? Okay. So this is the scene of tetrahedral. You can see that the case is reversed. Now we have 3 orbital on the upside and 2 orbital on the downside. Now what can be inferred from this about the ligand approach, whether it is axial or between the axis? See, all the orbitals which are between the axis are being lifted by energy, whereas which are along the axis are lowered in energy. So you can say very confidently that the ligand were approaching between the axis, and due to that reason, the repulsion between the metal ion electron and metal ion d orbital electron, and the electron of the ligand that is approaching have increased, and we can see that the lobes which are between the axes are increased energy. So is this point clear? Okay, so this is about the tetrahedral splitting. Now we will move to color. How is the color decided? Okay, how do we decide the color in the case of coordination complex? When do we see color? What is the reason behind it? So the reason behind it is the DD transition. So there are three factors. So now today we'll stick to DD transition because it is the one that is according to your syllabus. So what happens is that you have seen the splitting. You have seen that some electrons are in the low orbital. So when they jump from a low orbital to higher orbital, there is a transition between one d orbital to another d orbital, and that is termed as DD transition. And when they revert back, okay, when they revert back, there is a release of energy in the form of light, and you see the colored complex. Okay, so the main reason behind the color of this coordination complex is the DD transition. Okay, now one very important thing. Okay, so one very important thing. Suppose you know Vibgyor. Okay, so suppose I just draw it all in the form of a spin wheel. This is V. I will drop off indigo, then G, Y, Vib. Okay, so I think I've drawn one more. I've drawn an extra. Again, let me draw it. Now, V, B, G, Y. Okay. So the point I'm trying to make is that suppose violet color is absorbed, then the complementary of that color will be released. Okay, complementary of that color is released. So this is the thing. So if yellow is absorbed, violet will be released. If blue green is absorbed, red will be released. Blue is absorbed, yellow range will be increased. Yeah, if it is ultraviolet, pale yellow, red it is blue, blue green it is violet. So this is very important. Okay, so the one that is absorbed, the complementary of that is released. So how do we do it? Okay, so let me draw it on a screen. So it's very interesting. I'm not since I'm not getting it, I will try to draw it. So how many compartments we need? V, B, G, Y, O, R. We need six compartments. So 2 compartments, 4 compartments, and 6 compartments. So V, B, G, Y, O, R. Now it is good. Okay. Now suppose yellow is absorbed, then violet will be seen. If blue is absorbed, orange will be seen. If green is absorbed, red will be seen. Okay, so this is very interesting way to write this thing. Okay, clear? Okay. Red is blue. Okay. One more thing. I think here I will be there. I, B. What about violet? It's violet, yellow. Yeah. So this is your circle. Violet, indigo, blue, yellow, orange. So if red is absorbed, blue will be seen. If blue absorbed, red will be seen. So these are all the complementary of each other. Okay, so you can use this wheel to learn this thing. Now, the color in the coordination, suppose we have TiH2O6 3+, which is violet in color. So this is a D1 system. Okay. So T2J level in the stereotype complex, the next higher is EG level. Now, if the light corresponding to energy of a blue-green color is absorbed, it would excite the electron from T2G to EG. Okay. So if we just try to draw it for Ti3+, so it is T2G, 1 is there. Okay. Now it will absorb energy and one electron will excite to a higher energy. Now when this will come back, a violet color is observed. Why? Because the adsorbed color was what? The adsorbed color was violet color. Okay. No, the adsorbed color was blue-green region. Okay. The crystal field theory attributes the color of the coordination to the DD transition. See, this is the DD transition. So initially this is the ground state of the coordination compound. When it gets energy, the electron here excites to the EG level, and when it comes back, this will release energy in the form of a light. Okay, and hence you will see light, and the light that is being absorbed the complementary to that light, it is being released, and the color we see is that complementary color. Okay. Now it is important to note that in the absence of ligand, the crystal field splitting does not occur and the substance is colorless. See, it is colorless for the case of if it is not having any ligand. Now the influence of the ligand on the color of the complex may be illustrated in the case of NiH2O 3 plus. So if it is dissolved in water, it becomes colorless. Okay. Now, if the dye-dependent ligand ethylene 1-diamine is progressively added in the molar ratio, the following series of reaction and the associated color change is seen. So see, we have green color. It turns to pale blue. Okay. And if it is this ethylene diamine is added, it turns to blue purple. Again, this is the thing, and this is NiN3. So as we keep on upon adding this En, we can see that the color change is observed. Okay, from green to pale blue, pale blue to blue purple, and then at the last we have this. Now, what is the reason behind it? Because the ligand is changing, and as the ligand change, the field, the splitting amount energy is changing, and hence your color is also changing, because now different color, different region of color is absorbed and different color is released. Okay, so this is the color that we're talking about. Now, although it is able to explain all of this, but it has again some limitation. First of all, it does not take consideration about covalent character. There is a covalent character, and it is not completely based upon your bonding. Okay, ionic bonding. Okay, one more thing I just left is that how you will calculate your magnetic moment. It will be root under n into n plus 1. Suppose I take the case of TiH2O whole 6 3 plus. So it is T1. So number of unpaired electron is 1. So root into 1 plus 1. So that will give you root 2. And the root 2 is your magnetic moment in terms of mu. After that, I will talk about metal carbonyl. So the homoleptic carbonyl are formed mostly by the transition method. Homoleptic carbonyl means only carbonyl is present as the ligand. These carbonyl have simple, well-defined structure. Example is tetracarbonyl nickel is tetrahedral, pentacarbonyl nickel is trigonal bipyramidal, whereas hexacarbonyl chromium is octahedral. Similarly, decacarbonyl dimagnesium is made up of 2 square pyramidal joined by an MN-MN bond. So you should remember this also. There are 4 to 5 examples of carbonyl compound. You should try to remember the shape of it. Next is octacarbonyl dicarbonate, that is built by bridge of 2 carbonyl group. Okay. So this is the structure of all of this. This is homoleptic nickel carbonyl, then FeCO whole 5. This CO, this is bridging between these two. Okay. Here in this case, you have 2 trigonal bipyramidal, and this is octahedral. The metal carbonyl bond in metal carbonyl possesses sigma and pi bond, right? The metal carbonyl sigma bond is formed by the donation of lone pair of electrons on the carbonyl onto the vacant orbital, and the MC is formed by the donation of pair of electron from d orbital into the vacant pi star orbital of the carbon monoxide. See, what happens is that the carbonyl has electrons. So when the carbonyl donates, we will see a sigma bond, and when the metal donates as electron to the carbonyl, we see a pi bond, and the electron is donated in the pi star bond orbital of the carbonyl compound. The metal to ligand bonding creates a synergic effect, because both are just you can say stabilizing each of these. Okay, so you can see here, this is called a synergy effect. Carbonyl is giving electron to metal, and metal is giving electron to carbonyl, and this creates a synergy, right? Now, if I talk about the application, so the most important application is EDTA. This EDTA is used in purification and quantitative analysis, right? And this is the only hexadentate ligand. It's in diamine tetraacetate. Also, it is used in metallurgy and industrial and medicinal purposes. Okay. So you can just read about this. You can read this slide to get an idea about the application of coordination complex. So hardness of water is estimated with the help of titration of EDTA. The Ca2 plus and Mg2 plus ion forms a stable complex. The selective estimation of this ion can be done due to difference in stability constant. Okay. So you can just read this all. I'm not going through all of this. So with this, we have completed the coordination compound. In the next class, we will do exercise of the same compound. Clear? Of the same chapter. Okay. Thank you for this lecture.